Welcome to the 49th Theoretical Physics Colloquium by Professor Chun Shen from Wayne State University. He received his PhD in 2014 in Theoretical Physics from Ohio State University. During the last year of his PhD studies, he received Elizabeth Clay Howard Presidential Fellowship at the Ohio State University. After that, he got a postdoctoral fellow position at McGill University, where he spent 2 years between 2014 and 2016. In 2016, he received Goldhaber Fellow position at Brookhaven National Lab, where again, he spent 2 years before receiving a faculty position at Wayne State University in 2018. In 2015, he received APS Dissertation Award in Nuclear Physics from American Physical Society, the citation read, for his successful prediction of anisotropic flow in lead-lead collisions at the LHC, his elucidation of the Dirac photon flow puzzle, and his contributions to the development of a computational tool of viscous fluid dynamics enabling precision studies of relativistic heavy-ion collisions. He also had an offer of Oppenheimer Fellowship from Los Alamos Laboratory in 2016, which he declined, taking the Goldhaber Fellow at Brookhaven. His research interests include precision fluid dynamical models of Quark-Gluon Plasma at finite baryon density, jet and electromagnetic tomography of strongly coupled systems, rapid thermalization of out-of-equilibrium physics of many-body QCD, gluon saturation, and 3D imaging of nucleus at high energy, and many other things. And today he will be talking about multi-messenger heavy-ion physics. And with that, I'll give the microphone to Chun.
So thank Igor for the invitation and kind introductions. Let me start sharing my screen. So today I would like to actually talk about how to view heavy ion physics in a multi-messenger manner. So let me start with a brief introductions about why we're interested in studying the phase of matter. So in the daily life, we actually are familiar with matter in its different shape, for example, solid, liquid, and gas phase. And we know that if we keep increasing temperatures, the electrons inside the atom will be stripped off from its nucleus core so that they become freely move, not bound with the nucleus. So in that case, we will actually have a new state of matter called plasma, which is actually exists in the center of the sun in the temperature regions about 10 to the 5 to 10 to the 7 Kelvin. And actually the plasma phase actually exhibits lots of different properties compared to the regular liquid or gas phases. So that's actually interesting phase in the physics to study that. So following this logic, we would like to see that if we further increase temperature, say trying to heat up the core of the nucleus, then we'll actually try to actually understand the structures or the fundamental building blocks inside the nuclei, which is the quarks and gluons, which lives in a length scale of about 10 to the 15 meters in this scale. But it's not that easy to actually strip off individual quarks and gluons by increasing temperature and trying to separate them like the regular plasma phase. That's because the color confinement, because when you start to pull a quark away from the protons, the energies you start to put in actually increase linearly with the distance between them. So at a certain level, you will get enough energies to create a new quark-antiquark pair so that you can actually form two compound of the hadronic states of quarks and gluons. So that is not easy to actually separate individual quarks from the nucleon in the low temperature. However, in the very high temperature, there is a different phenomena happening, which is called color screening. So in a kind of pictorial way, if we look at the potential between quarks and antiquark pair, which actually in the low temperature phase, it grows linearly as the distance between the pair. But if we further increase temperatures by higher than some critical temperature, and it's to see that the potentials actually become more and more like a Coulomb potential, where in the long distance, it's become flattened out to be a constant value, which means that the force between the quark and antiquark, which is the derivative of this potential, becomes smaller and smaller. So in a pictorial way, this can be kind of illustrated in this formula, in this cartoonish picture. So in the low temperatures, we have a kind of a string-like fields between the quark-antiquark pair, which actually kind of bound our fundamental particles together with each other. And these forces increase linearly with each other. But if you have put this pair into a high temperature environment, where the temperature is high enough that you can produce quark-antiquark pairs in the vacuum, so that these additional pairs will actually randomly kick these color fields between this quark-antiquark pair, and then basically weaken the force between this original pair as they're falling apart from each other. So I think you can imagine that if the temperature increase to high enough temperatures, you can actually have a kind of free states of quarks and gluons, which doesn't bound with each other in bound states anymore. So how high will be that temperature that we can actually reach this conceptual kind of scenario case? So that actually rely on to actually compute such kind of thermodynamic properties through the underlying physics govern this interaction between quarks and gluons, which is called quantum chromodynamics, in short QCD. So using lattice techniques to put this theory on the computer, we can actually calculate the thermodynamic properties of a thermalized bulk of matters of these quark and gluons. And this theory actually predicts that at around this temperature around these regions, if you look at the degrees of freedom resistance, it actually rapidly increased from order of 10 to about 50 at the high temperature phase, almost a factor of 5. If you look at these temperature regions. And this smooth rapid crossover indicate that the system going through a rapid phase change from hadronic matter dominant like the nucleons and meson gas to a kind of system that's governed by the fundamental degrees of freedoms quark gluons in the high temperature regions. And if we want to translate these temperatures into the natural units that we are familiar with in daily life, for example, Kelvin, we can use this pocket formula to actually translate 1 mega electron volts to about 10 to the 10 power 10 kelvins. So this temperature here is about 2 trillion degrees of temperature or 1.5 trillion degrees of temperatures. So this is really extremely hot compared to our regular temperatures that we feel in our daily life. And the lower down, so if you can also translate that temperature into a pressure, so somewhat just like trying to squeeze all these nucleons together to form these super quarks and gluons, which we call Quark-Gluon Plasma. And the pressure you need is about 10 to the 30s of the atmosphere pressures. So this temperature or trillion degrees, Kelvin degrees of temperature, or this type of pressure is actually very extreme in our natures, that it doesn't exist naturally in anywhere in our universe. So this only exists at the very early stage of the universe, about a few microseconds away from the Big Bang, when this kind of state is macroscopically exist. So however, we can actually recreate such kind of extreme conditions through particle accelerators. So here we can accelerate heavy nuclei to near speed of light to actually collide with them. So that we can create microscopic systems that can achieve such high temperatures. And these experiments actually is routinely produced, conducted at the Relativistic Heavy-Ion Collider at the Brookhaven National Lab, indicated here, and also Large Hadron Collider at Chun. So let me just give you an illustration what the individual heavy ion collision look like. So we have two heavy nuclei like gold or lead nucleus, and they first are accelerated to very high speed, near speed of light, say 0.9999 times of speed of light. So you can kind of imagine there will be Lorentz contracted along the direction they accelerate with their velocities. So after they collide, there will be an extremely high density phase when these two nuclei overlap. And this produces so-called Quark-Gluon Plasma, which will then freeze, expands, and cools during the sequential time after the collisions. So here is a cartoon that kind of animation that we generate from the real simulations that I did with my colleagues a few years back ago. So we have two nuclei collide with each other, and after the collisions, you will see that the high density phase of the system will expand and cool smoothly, while you actually convert the collided energies into particles, new particles, through the Einstein equation like E equals mc squared. So the energy of the collision energy will produce a lot more new particles that actually will fly to the detectors. And from these simulations, you actually can notice that if you follow one of the nucleus along the longitudinal directions, you can actually see the literally the relativistic time dilation effects as the configurations actually freeze for a while before it actually evolves as a function of time. So in experiments, we do actually find kind of detect in one heavy collisions thousands of tracks of particles, charged particles, fly out of the detectors. And this can be actually see, this is an event display from the CMS experiments at CERN from a lead collisions at 2.76 TeV. So you can see there's thousands of charged particle tracks coming from the detectors, just coming from these heavy ion collisions. So let us now go a little bit detail into how the system evolves as a function of time through these heavy ion collisions. So we initially have two highly accelerated nuclei collide with each other. The system goes through some pre-equilibrium dynamics to reach a phase that the system is close to equilibrium, where the degrees of freedoms of the system is described by quarks and gluons because it's in the high density phase. As the system expands and cools, it will smoothly cross the QGP phase to hydrogen gas phase, where the temperature or energy density is lower than the critical temperature or energy density predicted by the latest QCD calculations. Then where the partons will actually combine or kind of combine fragments into hadrons. And then these hadrons will continue collide with each other until the density becomes so low, and then particles stop to interact with each other and fly to the detectors. So there are a few things I want to first comment is that these complex dynamics I just explained actually happens in a time scale of yoctoseconds. So 1 yoctosecond is 10 to the minus 24 seconds, which is a very short time scale. So this means that the complex dynamics of heavy ion collisions happen really extremely fast. And the size of system is actually extremely small, which is about a few times size of the nucleus. So this actually poses extreme challenge to actually understand the dynamics happen for these systems from experimental view, because you cannot shine laser or other external probes to actually probe such fast dynamics, because it's not fast enough to actually resolve any stage of that. What can be measured at the final state is only the ashes of these heavy ion collisions. And we need to backtrace to the early stage to infer the dynamics happen in this case. But there's also another aspect of heavy ion collisions is because, as you notice, that at the end of the collisions, we have a variety of particles actually emitted from the collisions. We have hadronic particles like mesons, kaons, or regular protons, but as well as some other electromagnetic particles like photons and dileptons. So those particles are actually carry different, they are emitted with different natures through these collisions, so they carry different types of informations. So this actually, the combination of all these particles are determined, I would say, the multi-messenger nature of the heavy ion physics that we would like to study. So by combining to look at all these different species of hadrons and photons and dileptons together, we'll learn a lot more information about the dynamics of heavy ion collision. So let me now just draw a brief analogous to the multi-messenger astrophysics that has been actually advertised a lot in the literature, in the astronomy fields. So as we know that in these decades, we have a lot of different probes to actually probe astronomy objects far away from us. The most kind of accurate is the cosmic wave background. So from measuring the photons coming towards us and actually trying to measure the temperature fluctuations on the sky from the Big Bang. And also occasionally we have high energy cosmic rays actually can go through our Earth and then being detected. And there's also other type of species particle like neutrinos, which doesn't interact with the other particle very a lot, so that they carry different type of information compared to the photons coming from the early stage of the universe. And nevertheless, we have also gravity wave, which actually help us to understand even primordial informations about the Big Bangs, potentially in the near future. So I want to now try to actually draw the next to heavy-ion physics. So I would say that in heavy-ion physics, photons in astronomy is much like hadrons in the heavy ions, because the hadrons actually keep intact with each other for a while until the density of the system become low enough so that their momentum informations freeze. And then by measuring the momentum information of those hadrons, we're essentially building up the CMB for the heavy ion physics, which actually we try to study fluctuation, the correlations of these momentum distribution hadrons to infer the initial state fluctuations. The high energy cosmic ray, in our case, will be actually a kind of remnant of the high energy QCD jets, which punching through the QGPs, which lose energy and modify their shower shape. So we actually, so I think this has a good analogous to that. And the neutrino physics in the astronomy is actually very similar to the ENM radiations that were actually discussed today, most focus on this aspect, that they actually carry more clean and penetrating probes for the systems from the early stage. And last but not least, let me actually say that since the gradual wave is kind of trying to provide information about the early stage of the Big Bang, in heavy-ion physics, we have also electroweak bosons, which is also really sensitive to the early initial stage of the collisions. But since they also only interact electromagnetically through the systems, they will also be less sensitive to the later stage of the evolution. So what I like to do in heavy-ion collisions is trying to use the experimental measurements to define the properties of Quark-Gluon plasmas. So what I want to do is want to understand the hot QCD phase of the hot phase of the QCD. For example, the equation state of this how the nuclear matter behave. For example, a function of temperature, energy density as a function of temperature or speed of sound, as well as the transport properties of the Quark-Gluon plasma, like viscosities and diffusion constant for charges. And also, as well as we want to see how at high temperatures the QGP can shine out lights, as well as interact with strong electro probes like quarks and gluons. So there's different types of experimental measurement associated with those quantities, which are mostly sensitive to that. But however, heavy-ion physics knows that easy because all these different aspects are not decoupled from each other. However, they have interlinked with each other. For example, the bulk evolutions will affect the ENM emissions as well as energy loss by a lot. So that really relies us to actually connect all these variables in terms of one single theoretical framework, trying to study all of them and the correlation between them. So one of such framework has been developed inside our heavy-ion community, which is led by the JETSCAPE collaborations, trying to unify the physics between different types of probes into one unified framework or unified event generators. Then actually can help us to to actually describe all different types of the experimental observables that I listed before. So this is already kind of an open source framework that can be actually used and benefit from the community. So now let me kind of use one kind of experimental figure trying to represent the multi-messenger heavy-ion physics, which here I choose this RAA, which is the nuclear modification factor for different species of particles. So here is the RAA measurement at RHIC for photons and charged particles. And here is the measurement at LC for charged hadrons and also electroweak bosons, and showing here. So as you can see, based on the different types of species particles, their natures, for example, electroweak probes that we are less interact with the medium, they actually have very small electromagnetic modifications with compared to the PP baseline. But however, you can also see there's enhancement due to the thermal radiations. But hadrons will have a very different behaviors for this RAA in the AA collision compared to the scale PP measurements. So I would say that different species of hadrons actually carry different types of informations as shown here. And this talk, I will mostly focus on the soft particles, which are the particle who has a momentum smaller than 3 GeV. So they actually made up 99% of all the measurements, all the measured particles in the experiments. Although in these figures, they only contain a very small phase space because of the choice of the linear scale of the PT. However, this will be a majority of particles that has been detected in the detectors. So the reason I want to focus on the soft particle is because they build up the energy momentum tensors, the whole thermodynamic dissipative properties of the systems in the heavy-ion collisions. So that's kind of the properties we are interested in and we would like to study with. So for the soft probes, there are two types of probes in heavy-ion collisions. So there is a type of called electromagnetic radiations, which happens going through all stage of heavy-ion collisions, from the initial stage to the final stage. There is prompt photons as well as photon emit from pre-equilibrium stage. Once the system reaches near thermal equilibrium, as you can think about as a black body radiations, there will be thermal radiation coming from these hot mediums as it evolves through different phases. And later on, you have photons from decays of charged particles of hadrons as well. So these are actually photons and dileptons in this case are actually unique in their sense because they are soft, which means that they actually sensitive to the underlying dynamics, soft dynamics of the bulk medium. And they are penetrating because they only interact with the medium through electromagnetic radiation interactions, which are very weak compared to the strong interactions. So once they produce, they will actually preserve their momentum informations and fly freely to the detectors without further final state interaction. And the second species of particles are charged particles of hadrons emitted at the end of the evolutions when the density of the system becomes so dilute. And they basically are actually set free at the late stage. And since they go through the whole evolutions, they partially lose their actually initial memory of where they are or the informations about the early stage along the trajectories of their evolutions. So the goal is trying to combine these two types of species of observables, trying to infer different types of aspects of the dynamics in here. And they provide complementary informations that can help us to understand the soft dynamics as a whole, to give out the whole picture of the soft dynamics of QCD. So for hadrons itself, it's actually gained a lot of success over the years in our field. For example, here is an example that I show you that if you detect hadrons, it actually contains a lot of momentum information that can be analogous to the CMB analysis. So in the big bands, when we have the CMB measurements for the temperature fluctuation correlations, these will actually help us to understand the initial state fluctuations in the early stage of the universe. And similarly, we have in the heavy ion collisions, the initial state fluctuations in spatial in the spatial configurations are mapped through hydrodynamics to the momentum space, and eventually kind of detected by the experiments. And these VN coefficients, which characterize the momentum anisotropy of the particles in the momentum space, it will give us power spectrums to help us to understand initial state fluctuations and also the medium properties. One of the success of the analysis in our field is to perform a global Bayesian constraints to trying to constrain the QGP viscosity, bulk and shear viscosities using the hadronic observables. For example, here is a study done by the recent study done by the JETSCAPE collaborations, trying to use the measurements, the accurate precision measurements from charged particles yield in PT and anisotropic flow coefficients at both RHIC and FC energies to constrain the QGP transport shear and bulk viscosities. As you can see that we can use this data to constrain from the prior indicated in the gray area to the blue distribution of these. And is the
Chun?
Multiple and complex, yes.
There is a question here. Rajiv, go ahead.
Yeah.
Okay.
Yeah, can you go to a previous slide? Previous page. Yeah. So I have a question, basic questions, like how did you, how experimentally you got the information that these structures about the V1, V2, V3, means how anyone decide or how anyone got this idea of this flow structure?
So in the experiments, you can measure those flow coefficients using so-called two-particle correlations or multi-particle correlation method by looking at the angular distributions of two-particle or multi-particle correlation functions. And they can be expanded in a Fourier series, and the Fourier coefficients represent these Vn coefficients. In the hydrodynamic simulations from theory, what you can see, what you can learn is that those anisotropic flow coefficients has at least the lower order, say V2 and V3, are linearly correlated with initial shape fluctuations like the elliptical shape or the triangular shape of the initial state fluctuation. They have a linear mapping between these two quantities. So that gives you idea that these measurements actually can help us to constrain the initial state shape fluctuations in the heavy ion collisions.
Okay, thank you.
Okay, so yeah, so I would say that the Bayesian analysis that in our field become more and more become a standard way trying to constrain physical quantity like QGP viscosities through multiple data set comparisons. So now today I want to actually focus on a different aspect by basically looking at using photons and dileptons as a microscope to understand detailed structures of the QCD matters, go beyond just understanding the microscopic properties from the hadronic observables. So from the right-hand side, I want to just draw a simple argument is that if you look at photon productions from, say, Quark-Gluon scatterings, mainly dominated by this T-channel process, the photons momentum distributions can be approximately follow the momentum distribution of the incoming quark in this case. And this tells me that if I measure the photon momentum distributions, they will reflect more or less the underlying quark momentum distributions of the fluid. So that's kind of the information that cannot be get easily from the hadronic observables, but actually can be provided by the photons. So if you think in this way, then we can actually also see that there's a different nature of electromagnetic probe productions compared to hadrons, because they actually emit through all the entire phase space, space-time volumes through the heavy ion collisions, while hadrons only emit at the end of the freeze out. So here I want to show you animations of the same hadronic fire, the same hydrodynamic fireball simulations of the energy densities, and trying to show you the hadronic emissions on the left compared to the photon emissions on the right. So as you can see, as the fireball evolve, you can see there's a lot of photons emitted at the early time, whereas there's relatively less hadrons emitted at the very early time in these heavy-ion collisions. And hadrons only emit on the hypersurface, Friedel surface, which is indicated at this white contour here, while photons are emitted all inside the fireballs at the high temperature phase. So this actually reveals different nature of photon emissions compared to hadron emissions in heavy-ion collisions. And we would expect to expect that the photons will carry different type of informations compared to hadrons in these heavy-ion collisions. So here's a cartoon that's showing you that so really the photons actually emitted through all different type of phases. If you plot the contour of temperature as a function of tau, and you will see that the photons can emit it all the way from these different phases, where hadronic particles are only emitted at the late times at the very low temperatures. So this in this sense that photon actually probe the inner working of the QGP phase more directly compared to hadronic observables. So if we do so-called to look at where does most of the photon emits in these heavy-ion collisions, so this is so-called thermal photon tomography. We will find that from the theoretical calculations, there seems to be a two-wave structures of photon emissions. First, at the very early time, at a very high temperature, because if you think about Stefan Boltzmann law, that the thermal radiations go like T⁴ horsepower. So actually higher temperature fluid cell will emit a lot more photons compared to lower temperature. So that's actually the first wave of the photon productions at a high temperature. And also we also notice there's a second wave of photon productions near the phase transition values where the speed of sound is actually minimal compared to the rest of the regions. So these regions actually, this is reflect that there's a big volume of the space-time volumes here to allow for more photon emits from the medium. On the right-hand side, I show you where does the photon elliptic flow, the V2 coefficients of photons come from through this analysis. And you can notice that most of the elliptic flow of photons actually generate in these transition regions between 150 to 200 MeV in terms of temperature, or 3 to 8 Fermi in terms of lifetime. So the hadronic VNs actually is actually generated at the very low temperatures, around 120 or 130 MeV, which is much lower than the photon photon temperature here. So in this sense, that the photon VNs, V2, will actually carry more information about how the flow is in the patterns in the transition regions, different from hadronic VNs. However, there's also kind of effects called so-called Doppler effects in heavy-ion collisions because our heavy-ion collisions is strongly expanding. So the strong flow velocity will actually boost the particles that's emitted. So this is much like kind of surfing on the sea, like individual particles like photons and heavy hadrons are like these individual surfers. They're actually pushed by the global wave generated by the hydrodynamics. So from this simple formula, so these P.U factors here are kind of encode these kind of local boost from the radial flow to the photon spectrums. So the temperature generated from these photon spectrums are kind of blue shifted by the Doppler effects with the radial flow, hydrodynamic flow of the underlying hydrodynamic flows. So in this sense, we cannot directly read off the temperature from these thermal photon spectrums, if you think about in the sense of black body radiations. So those spectrums, although they look like has an exponential shape in the low PT, but they actually encode not just temperature, but also Doppler effects from the blue shades. So how should we actually extract useful information from this slope of the photon measurements? So we can actually take a closer look and the experiment and the simulations, trying to understand the slope of these photon spectrums. So if we use just the photon spectra, looking at those photons emitted at the different temperature windows, the 2 temperature windows, and look at their photon spectra in the realistic simulations, where the flow is actually fixed by the hadronic observables, we can actually make this kind of map between the real temperature of the fluid cell where the photons are emitted versus their boosted temperatures that actually you can see observed from the detectors. What you can see is that at the high temperature phase, because most of photons are emitted early, where the radial flow hasn't developed yet, so the temperatures from the thermal photon spectra is actually follow very closely to the true temperatures until about like 270 MeV in the RHIC case, and about 300 MeV at the RHIC case. At the lower temperatures, you can see that most of the photons actually blue shifted. So you can see that these dots doesn't follow this black dashed line anymore, but actually blue shift to this 250 MeV roughly at the RHIC energies due to the radial flow. And this drastic blue shift effects is due to the strong radial flow provided by the heavy-ion collisions. And this happened for both RHIC and RHC energies, as you can see that these blue shift effects really influence the low temperature photons below 250 MeV in here. So the current experiments find that the fits to the slope is consistent with the blue shift temperature, which is hard to actually help us to identify whether this temperature is due to the blue shift or just really coming from the true temperature part. However, if we can actually get the higher slope of the photon spectrums in somewhat higher PT or early photons, then these temperatures actually will less affected by the hadronic radial flow, and they will more or less reveal the true temperature of the system in this case.
We have a question.
However,
here.
The temperature, yes.
Go ahead.
Yes, hello, Henry DeYoung. Maybe I'm not understanding, but you have a Doppler shift effect, and in your diagram, when after the collision, you would have. Are you measuring this total electromagnetic output over the whole volume of the collision, or each portion of it, or how do you accommodate for this this collision, because you have 2 different Doppler shifts here?
So yeah, so what you can measure in the experiments as the integrated results from everything emitted. So it's very hard. It's very since all the dynamics happen in the Yocto scale, second scale. So it's impossible to actually measure the delay between different phases of photons coming on different times. So what you can measure is all the integrated values. So everything emitted will be actually measured at once. We cannot resolve which photon come earlier than the others. So that's the challenge in this case, because if we can only measure the early photons, they will have the real temperatures from there. So the real experiments is kind of convolutions of all these calculations to get the final results in there.
Thank you.
So every fluid cell will have different blue shifts. I need to integrate them together to get a final result.
Chun, there is another question in the chat message, so I'll read it for you. Do you think thermal photons can also come from giant dipole resonance? Can these photons be coherent states coming from Graziano Mileto?
So there's no, so in heavy-ion collision, there's no giant dipole anisotropy compared to the CMB yet. But in there, so basically this. So mostly the photon productions is just coming from like thermal radiations that in our calculations. It's mostly dominated by this case. I'll talk about the other kind of mechanism later on, so that you will see that there's also new kind of way to produce photons or influence photon observables. Yeah. Yeah. So since the PT spectra of the photons actually is influenced by the radial flow, so we'd expect that if we look at the integrated yields, then they will be less affected by the radial flow, because if we integrate over the whole PT, then it will be immune by the blue shift effects. So here we can actually integrate a range, cannot integrate for the whole range, but just a PT range of the photons, and look at its centrality dependence compared to the charged particles. So here is a calculation versus the experimental measurement from Phoenix and Star at 20 dB. The experimental data has some discrepancy, which will be resolved in the near future, hopefully. And but the message here is just saying that if you look at the thermal photons compared to the charged particles, the increased yield is actually more rapid for the photons compared to the charged particles. The power law is about 0.25 if you look at the slope here. So for the direct photons, it actually contains two main sources. One is the thermal photons, and the other is the prompt photons coming from the initial collisions. For the thermal photons, if you look at the central dependence compared to the charged hadrons, so photons emitted in the 4 volumes, which we need to be weighted with the Stefan-Boltzmann law rates, which go like T to the 4th. And for the hadrons, it's basically the local entropy density times the 3-space volume on the hypersurface. So if you do some math and then do some approximations, you can arrive some pocket formula. Understand that these ratios will actually go like increase as average temperature or the lifetime of the fireballs. So as you can see that if you go to more and more central collisions where the fireball has higher average temperatures or longer lifetimes, you will actually get higher values. And these experiments and the data comparison just tell you that this actually is going to the correct trend. And for the prompt photons, it's actually scaled with number of binary collisions, which produce these prompt photons. And you can assume that the number of participants go roughly with the charged hadrons. So this go with a lower power as indicated here. The 4 calculations combine these, both of them actually agree roughly the trend of the experimental measured trend here, which suggests these thermal photons actually give you this interpretation is actually sensible in this case. And this can be also has been pursued if you look at thermal dileptons in the low invariant mass regions, so that you can actually, in this case, that in these low mass regions, the average temperature of the system is roughly the same, or in hadronic temperature window. So the mainly kind of knob that you will evaluate as a function of root S is mainly just the lifetime of the fireball. As in this study, people actually show that the calculation show that this excess of the dilepton yields, so dilepton yields is actually has a very strong correlations with the lifetime of the fireballs, which can be hopefully to use as a clock for the measurements of heavy-ion collisions. And this is actually being measured by the star collaborations of the thermal excess of the dilepton yields at different collision energies, showing on the left. So in these low mass, invariant mass regions of the dileptons, you can see there's some excess of the thermal dilepton yields. And if you extract these yields and plot a function of d and data, you can actually see these kind of, there's a hint of the rise of the data despite of the large error bars. And this actually can be correlated with the lifetime of the fireball in hadronic phase. So if you want to really get the temperature information from the median from experimental measurements, you can actually look at the dilepton spectra in the intermediate mass range. So here is a measurement of the thermal dileptons in the Indian collisions by NA60, where they basically subtract all the backgrounds and then give the thermal signals in these black dots. So for the high invariant mass, most of the dileptons will be emitted from the Quark-Gluon Plasma phase, as indicated by this calculation as this yellow line here. And the hadronic phase, the dileptons will be in this dashed line. So by looking at the spectrums, the invariant mass spectrums, you actually is immune by the blue shift effects in the case. In this case, so you can actually use this invariant mass spectrum to directly read off some average temperature of your mediums. And in this case, the temperature is about 170, which is around the pseudo transition temperatures provided by the lattice QCD data. And they also here is also calculate this did this exercise for the higher energies, where these average temperatures in these intermediate invariant mass regions will actually increase to about 200 MeV, which is the average temperature of the fireball, in this case, measured by the dilepton spectrums. And this certainly is lower than the initial temperature indicated as this purple line, but this is actually a true temperature measure if they can, experiments can measure these intermediate mass thermal dilepton spectrums. So this actually serves as a really a good thermometer for the QTPs. Okay, now the second story I want to tell you about photon analysis is trying to looking at early stage of the collisions. So if we look at the photons at different PT cuts, for example, a very low PT, then you see that most of the photons are coming from the phase transition regions. But if I increase the PT values to the high PT, say 2 to 3 GeV, and you can see that there's a lots of photons coming from early state at very hot temperatures at very early time. So these high PT thermal photons actually give us a window to understand the early state dynamics of the systems better than the hadrons. So in order trying to build up such kind of simulations, we need to have a realistic pre-equilibrium state for the simulations. Here we use a model which contains this new pre-equilibrium state, which is named by the model named by the compose, which connect the initial state modeled by some color glass condensate effective theory with hydrodynamics and overall with the transport. So we first basically tune our simulations to reproduce all hadronic observables in the central collisions. As you can see, the multiplicities from solid and dashed lines more or less with each other, as well as mean PT and the flow, hadronic flow measurements. And I would like to ask, what does the photon will say for this different initial pre-equilibrium phase for these measurements? So we compare this exercise at both RHIC and C energies for direct photon spectrum and their anisotropic flow for different centralities. As you can see that by using different pre-equilibrium stage, direct photon spectrum yield and V2 didn't show much of the difference once you constrain the simulation by the hadrons. And this story is true for both RHIC energies as well as at LC energies. So both calculations with without this realistic pre-equilibrium stage will actually give you more or less the same kind of evolutions. However, in this case, we can also look at a different type of early stage effects, which is basically look at the chemical equilibrations procedures. Because in the early stage, we will think about the system will be mostly dominated by the gluons. And the quark will be produced gradually through the collision during the early few times. So we basically use this kind of fugacity or suppression factors adopted by this paper to estimate how the quarks are dynamically generated as a function of pulsar time at the early stage. So we can introduce these two different functional form and look at the photon productions in the final states. So you can see that if we fold everything together, if you look at direct photon V2, you actually see a big sensitivity of this treatment of pre-equilibrium chemical fluid equilibriums using different treatment of the photon production at early stage. So in this
Chun,
case, I will say that, yes.
We have a question.
Yes, Chun. So you're not using compost to calculate the fugacity of the quarks, but you take an external input for that?
So this can be formally implemented in the compost by looking at this paper, but this is not numerically implemented yet in the public available compost version. So
okay,
what we
I
use
see.
is basically the scaling from the compost paper in this paper, and then putting by hand ourselves. But it would be better if in the future the compost is upgraded so that this is built in there and we can use that directly.
Thank you.
So this is a first step towards to this study. So yeah, the bottom line is that the direct photon flow at from 2 to 3 GeV actually show a big sensitivity to these early chemical pre-equilibrium equilibrations procedures that will be actually hard to get from hadronic observables. Okay, the last story I want to tell you about this photon hadron analysis is about kind of going to a small system. Like we know that the collective behaviors for hadrons persist as we shrink the system size from a big heavy ion collisions to a small p-led or pp collisions. And this sort of actually agree with the hydrodynamic simulations. But however, only looking at the collective behaviors cannot convince most of the people that that there's actually a hot QGP droplet exists in the small system. There could be other alternative scenarios that in the system, small system can cook up these collective behaviors. So, so here is also another example that we can even change the geometries from P-gold, D-gold, and helium 3 gold to look at the shape difference in these three different collision systems, and then to compare with hydrodynamic simulation. And this is done by the Phoenix measurements, which truly show that there is a hydrodynamic response to the initial geometry for these different type of systems. So the question what we would like to ask is, how about thermal radiation from this small system? Because if you have a hot systems present in here, it not only will generate hydrodynamic flow, but it will also generate thermal radiations. Just like you look at an object has a temperature, it will give you some thermal enhancement of the photon productions as well during the evolutions. So through the calculations, we can actually find that this thermal radiation, even this small volume of the phase space, actually is significant. If you look at 0 to 5% multiplicity events with highest multiplicity in these small systems. If you compare the thermal radiation from the system compared to the prompt collisions, the photon produced from the prompt collisions, actually it will shine out in the low PTs in these direct photon spectra. So what you can do is, calculate this RPA for this nuclear modification factor as a function PT for these four different type of systems. And we see a bump of this enhancement due to the additional thermal enhancement compared to the blue lines. So if we compare to the deco calculations with minimum bias, the data has large error bars, which hasn't been enough, has not been significant enough to actually tell us whether the blue curve or the red curve is preferred in this case at that time when we did the calculations. But however, the Phoenix collaboration take our suggestions and went ahead to actually measure the thermal photon productions in the central and 0 to 5% P-gold collisions. And here is the preliminary data in 2018. Although I will say that this doesn't give us a very confident conclusion that this thermal radiations is preferred than dashed line because of the larger systematic and systematic error bars. But this is really encouraging if by looking at these measurements that these actually do hint for a thermal radiations in these small central P-gold collisions. So as a series who actually did these both calculation for the VNs for the hadrons and also make the prediction for the thermal photons, when I look at these preliminary data, it's really encouraging to me that this actually is a really encouraging signal that that we may have something really interesting to see in this kind of combined analysis. So I would say that if in the future we have more precise measurements of the thermal photon in the low PT, they will actually give us very strong evidence about the hot QGP existence in these small systems. And this data cannot be directly get from the hadrons, but the thermal photons can give us a very much cleaner signatures about this statement. So over the years, there's also a lot of other development in this thermal photon dilepton areas. For example, we have emission rates that actually calculate from the lattice QCD, which give us more precisions or about the emission rates that we can use in the phase transition regions. The modification of the rho spectral functions in dileptons actually relate to the chirosymmetry fluorescence, which is a big question in our field, trying to answer how the median rho spectral function is modified in the presence of a hot medium. And there's also other new subjects that can be actually discussed using the thermal photon dilepton studies when we compare the data. But last but not least, there's also kind of scenario proposed by people that the early strong magnetic field can also influence the photon productions and generate some more elliptic flow to help the data to model comparison. That our chair actually is, one person actually did a recent calculation along this direction. But now let me kind of going back to the big theme of these multi-messengers. So what I have so far just show you that there's a combined access that we have done by combining hadron and photons that already can give us a lot of information. But there's a richness of the experimental programs in the future that give us more kind of promising measurements along the way. For example, at RHIC, there's an upgrade from STAR and S-Phoenix program to actually help us to not only probe the QCD matters at the finite baryon density, but also very high resolution jets and other rare probes to probe the QGP structure at the RHIC physics. Along the way, there's also LHC upgrades, which also give us the frontier of the high energy and high luminosity statistics for these rare probes and the measurements. And in the near future, there will be other experimental programs like Theia and Nika trying to probe the QCD matter at the large baryon density, and electron-ion colliders to help us to do tomography of nucleus with precisions. So I would say that all these detectors actually give us multiple data with precisions and really drive our field into a multi-messenger area, such that we need to actually simultaneously study all these probes to get the ultimate information for these heavy-ion collision systems. And this actually requires us to have a more dedicated theoretical framework trying to actually calculate all these observables in a unified way. So I would say that in the high energy density frontiers, there's effort, combined effort from the beam understand theory collaborations, in short, BAST collaborations, to develop frameworks to actually understand the three-dimensional dynamics, as well as other physics involved in the low energies, trying to understand the phase structure of the hot QCD matters. And this also will eventually follow with the next generation theoretical framework that will be led by the JETSCAPE collaborations in our field to fully embrace all different types of physics together in one framework and trying to kind of serve as open source event generators for the high energy communities to do all these different types of physics in a controlled way, so that you can actually import your physics yourself into this agnostic framework and also use other state-of-art development together to do the physics and extract information from that. With that, let me go to my summary. So as I can show you that there's a vibrant experimental program around over the world to provide us more and more precise measurements for different types of particles measurements in the heavy-ion collisions. And this really drives us to actually a multi-messenger area, so that we need to consider all these different types of probes simultaneously to gain insights for physics. And this is a challenge, but also an opportunity once we have a unified theoretical framework, plus some statistical tools that can help us to constrain these multi-dimensional observables and trying to systematically study physics in here. So what I have shown you in this talk is basically a kind of baby step, which combine hadron and photon analysis together to show you how it is a powerful tool to help us understand the soft dynamics of QCD matters at high energy. And in the future, I would say that if we can embrace more and more observable like in IPT together with hadrons and ENM probe, will actually help us to fully categorize the property of Quark-Gluon Plasma in multiple dimensions. So that's all. Thank you for your attention.
Well, thank you very much for a very nice presentation. Now we will have some time for questions. So any questions from the audience? Any questions from the audience? Please raise your hand if you have questions. I see claps in the audience. That's great. Okay, let me start with a question to break the ice first. At some point, you mentioned that dileptons are not very sensitive to the blue shifting effects. Can you, maybe I missed the logic of the argument. What exactly is the argument? They seem to be pushed by the same flow.
Yes. Yeah, so the dilepton has an additional dimension, which is called the invariant mass. So that's essentially integrated over the PT spectrum. So the invariant mass spectrum, in this sense, is immune to the flow boost effects in here, because the boost is always in the PT shape of the spectrum. But if you integrate the PT, then the invariant mass spectrum is immune to the blue shifts. So if you think about photon is like in the invariant mass equal to 0 limit, which only have 1 point, so that it's hard to get the temperature from just 1 point. But for dilepton, you have this extra handle of the invariant mass of the dilepton pair, which you can vary, and then you can look at this spectrum to extract temperature.
I see.
It's a much cleaner process, but also measuring the dilepton in this intermediate invariant mass is extremely challenging in the experiments. So that's kind of the challenge in the experiments to measure that.
Okay, great, thanks. Boris, you're next.
Yes, thank you. I have a question about, I think it was slide 53, the R the R factor for photons, I think in neutron gold, was it? Yes, this one. Oh, so R for proton gold. So what exactly is compared here? Because so sometimes also proton-proton collisions are interpreted hydrodynamically. So is this like a hydrodynamic proton gold to hydrodynamic proton-proton, and then where the bump is coming from? Is it higher temperature or is it more flow?
So yeah, so the experimental data is basically the direct photon spectra from proton gold in 0 to 5% centrality divided by the PP reference. So for the heavy-ion calculations, we calculate the PQCD expects, which contain the saturation, kind of the cold nuclear saturations, the nuclear shadowings in the cold nucleus. So that's kind of why these dashed line go to smaller than 1. So if you only have the cold nuclear effects, so you would expect this RP left will be below 1 in the low PT, but almost 1 here. And this bump here is mostly generated by the extra thermal radiations when you have a presence of hot QGP media. And having that said, you also mentioned the good point is that even in PP, there could be a potential hot medium in the PP calculations. And we also did the PP estimate for the thermal radiations. And this is showing here. So the PP case that the median is extremely small, so that the thermal radiations is still very small compared to the prompt source. So that will not change the ratios when you even assume that there's a PP median in there, so that this bump will still persist at around factor 2 here in the calculations. And this really is coming from the additional thermal radiations when you have a hot QGP median exist in the proton lab that give you this enhancement in this calculation.
Yeah, thank you.
Okay, other questions? I think I've seen another hand. No, I don't see it disappeared. I don't see any questions. Okay, Ulrich, go ahead.
Yeah, it's not a question. It was an additional comment about the question that you asked. It's just like when you take the hadron momentum spectra and you integrate over the momentum, the yields, they are completely insensitive to the flow. They give you directly the temperature at which the chemical composition was fixed. And when you look at the PT spectra, then you have to disentangle flow from temperature, and it then gives you a different temperature, namely when the energies were frozen out. And so dileptons, when you look at the dilepton spectrum for dileptons with a certain mass, like say near the phi mass, or like between the phi and the J psi mass in the intermediate continuum, when you look at the PT distribution, you will see the flow effects. But if you look at the mass distribution, which integrates over momentum, it's insensitive to flow. And so it's a clean measure of the temperature, and that's why this is interesting.
I see, yeah, thanks. Actually, I did have another question related to what Boris was bringing up. In fact, right, this slide is kind of perfect. When you are considering this thermal contributions or the thermal components of the emission from the small systems, I think it's a little naive to expect that you actually have a thermalized plasma there, right? So wouldn't it be better simply to consider a, I don't know, totally unequilibrated, some sort of random distribution of the particles? They will have the emission anyway. It's just the distribution function, which is not equilibrium. So is that what you are calling thermal, or what exactly is the thermal terminology here?
So yeah, that's a good point. So this actually assumes that the emission rates are coming from a thermal distribution. So if you have a kind of, say, non-thermal equilibrium distributions for the charge carriers, that still could potentially also produce photons. That's hard to estimate because the rates are hard to calculate. And also, but this one actually increased not only the perfect thermal equilibrium, but some of the off equilibrium is characterized by the shear stress tensor. So there's a viscous corrections to the particle distributions in these calculations, and the same underlying medium from hydrodynamic descriptions that are consistent to give this. So I would say that if you have some model give us some different random distributions, which could mimic this bump, you should also try to produce the hadronic VNs from these calculations, from that distributions. I would say that the only one signals of thermal enhancement may not be that smoking gun for the existence of hot UGP medium, but if you want to combine hadron and thermal photon together, they give us stronger evidence. So that's not easy to get both right with a different model.
Right. Well, the only reason I'm bringing this up, because naively, if you look at this plainly and reading the words thermal meaning thermalized plasma, people might jump to conclusions then, okay, I have this perfectly well thermalized plasma even in PP collision perhaps, or at least P nucleus collision, and that might be premature conclusion, right?
Yeah.
Okay.
So yeah, this is not exactly thermal. These already have some off equilibrium corrections already.
Right. Okay, any other questions? I really want other people to ask questions because I have plenty, and I'm not sure I want to take all this time. So I don't see any questions, any raised hands. So let me then push my question again. It's a different one related to the V2 when you were showing the, I don't remember which pages it was, I think a couple of pages back, where you were saying that there is this dependence on the models, strong dependence on the models of the early stages. I believe it was a different, this one perhaps. Now, even though you are saying that there is this strong dependence and you are trying to show the possibilities with these three different solid lines, solid and dashed dotted lines, they definitely fall very, very short of the experimental data, a factor of 2 short or more. So this alone cannot explain the V2, can it?
No, so still there are some still some inconsistency between the data to model comparison for the photon V2, especially for these 20 to 40% GO-GO collisions and high PD. Although the data error bar is large, but still it's kind of systematically the serial calculations is lower than the data, which might suggest there are some additional source compared to this standard treatment. For example, photons from early magnetic field, or photons coming from, say, transition regions when you have recombination of quarks and hadrons, when you could have additional photon productions. So those photons could carry large V2 and then eventually help you to increase the net signals up to where the data are. Yeah, but I would say that the plot we want to show here is just the net effect from this early stage chemical equilibrium, that whether or not there's additional source, this difference will be maybe somewhat diluted, but they will be still present if you treat the chemical equilibration differently at the early stage. There are still some remnants in these signals in here that will potentially help to probe the early stage dynamics.
Okay. Okay, that's fair. Okay, I don't see any other questions from the audience. So using this opportunity, I would like to thank you again for a very nice presentation, for taking time to organize this information in such a nice order. And thanks on behalf of everybody.